first course on material science, and this material science has two words, materials and science. What are these two words? We shall first try to understand before we proceed further. What we see around us is everything is a material, including the human beings, the flesh, the bones, the blood, the plants, the buildings, even the pen with which we write, or this remote control unit, everything is a material. Are we going to be studying every material on the earth? It's not possible in a one semester course. We restrict ourselves to inanimate solids, thereby I am eliminating all living things. Secondly, I am leaving out all liquids and gases, and then I am restricting these solids, inanimate solids, to be used by the engineer in the practice of his profession. I am not worried about something which is not being used by an engineer. These materials can be classified in number of ways. Of course, these days a lot of new materials have also come up. Basically, if I go in a conventional manner, one of the classification is metals and alloys. Metals, you know, copper, iron, aluminium, gold, silver, nickel, cadmium, these are all metals. Alloys, you have studied in school. An alloy is a combination of one metal with one or more elements such that the combination behaves like a metal. A metal-like behavior, as distinct from other materials, can be defined with the help of one single property, and that is the electrical resistivity of the material. Only in this class of material the resistivity increases with increasing temperature, while in all other cases it decreases with increasing temperature. Second category is ceramics and glasses. Ceramics is basically oxides and silicates like porcelain, china, and glasses, silicate glasses, the window panes you see, the windshields in the automobiles, they are all glasses, transparent materials. Basically the oxides and silicates. These are very hard materials, at the same time very brittle. The another classification is of organic polymers, which we are using more and more as the time progresses. We have got now even engineering polymers with which you can make gears. Some examples are day-to-day use: polythene, PVC sheeting we put on the cables, and tires, rubber tires you use for automobiles, trucks, tractors. Use the polypropylene for the bonnet of a car. You use polypropylene these days for the bumpers, dashboards. They are all organic polymers. One engineering polymer, one very good engineering polymer, Teflon, provides a frictionless bearings. Then we have next category in which I put semiconductors. These computers which we are using, these facilities and the remote control we have, they are all based on certain chip, that is silicon chip, silicon crystal, in which we have put certain impurities, and the material is behaving like a semiconducting material. Elements are silicon and germanium basically, which behave like semiconductors. There are number of compounds made from elements taken around group 4, like say for example group 4 and group 4 combination of silicon and carbon, silicon carbide also behaves like a semiconductor. One element taken from group 3, one side of the group 4, the other one taken from the right side of the group 4, 5, like you have aluminum phosphide. These act as semiconducting materials. Similarly, zinc sulfide, cadmium telluride, some of these materials which you have in light emitting diodes, the photocells, these are all these kind of compounds. Gallium arsenide is one very good material as far as lasers is concerned. We want to integrate it with the silicon chip. We have certain difficulties, we shall see what are those difficulties in the course. Then we have materials which are called composites. These can be called basically man-made materials. Some of these could be natural, we will see that. Metal ceramic composites, like you have the reinforced concrete cement. The building is made of reinforced concrete cement. You have steel rods with which you make the cage, and in the cage we pour the mortar containing the gravel, the cement, the sand, and this is what is concrete. Because steel bars have been put there, it is called reinforced concrete cement or simply RCC. Steel is from the metals and alloys. Steel is an alloy because the one which we use is mostly iron and carbon alloy, plain carbon steel, but we do have certain alloying elements as well, like manganese, silicon, etc. in the normal steel which we have. And this mortar which we have put the concrete is a ceramic material containing silicates. So this is a composite material made of metal and ceramic. Then the second category of composites taken from ceramic and polymers. Ceramic material, as I already said, oxide and silicate, glasses are ceramic materials. When I reinforce these glass fibers to the matrix of a resin, which is a polymeric material, it is a ceramic polymer composite. Fiber reinforced plastic, you use the helmets made of fiber reinforced plastics. Some of the automobiles have come up with their body made of fiber reinforced plastic. Fiber reinforced plastic is used in various other household applications, like the body of a washing machine can make out of these. Then we have metal polymer composites, like vinyl coated steel. Vinyl coating is done in order to save or protect the steel from rusting, because it does not come in contact with the environment. Or you have resin coated steel bars which are used for reinforcement, so that again it does not get rusted inside the concrete. If it gets rusted, the strength of the concrete can come down. So these are specific composites made by us to serve a certain specific purpose, and this is also called the man-made materials. So composites, we shall look into it briefly. Then what we use these materials for as engineers? What is the application of these materials? There are different applications we engineers are putting these materials to. One is the structure. By structure I mean something which is dead body, like a building or a bridge or a body of a car or a body of a ship or a body of an aircraft, that's a structure. And for making these structures, I can use these materials which I talked about. Then second category is machines, something which are mobile, like engines, gears, pistons, or something moving, no? So motors, these are machines, mobile components. Then we have devices, like you have a computer is a device, radio set is a device, television is a device. Reason is, it's just like some kind of a black box, one kind of an input and other kind of an output. So input is some signal and you get voice, you get the picture on the TV. That's a device. It's a small thing, but it does a function which is and converts the input, whatever is the input, into the output, which is a different one, altogether different from the input. Your transistor sets, the radios, the televisions, all these things fall in this category of devices. Now to make this, we make use of materials from all the categories. So for example, I just gave you an example of a structure, the building. Reinforced concrete cement has metal as well as the ceramic. The doors and windows, you make the door frame out of wood. The wood is a natural composite. Then you have the flooring, you can see this tiles, it's a polymeric material. You have soundproofing done, that's another polymeric material. So different materials are used to make one structure. Even for making a computer, I am using plastic, I am using metal, I am using semiconductors. So all various different kinds of materials are used for making one application. Okay. Then the second word in the course material science is the science. When we talk of science, chemistry and physics, because mathematics is also a science, is usually the connotation we get is chemistry and physics. Since we are talking about the materials which are solids, it should be chemistry and physics of solids. In other words, solid state chemistry or solid state physics. Both these subjects are very, very rigorous in their treatment, and as engineers, our interest is to see that material does the function, does the work, whatever application I put it to, whether my science is working rigorously or it is not working very rigorously. So we are trying to keep in mind the engineering usefulness of the material, and that is what this science is all about. I am not very rigorous, I may be using a lot of approximations, but as long as this approximation gives me the result with which I can predict that my material is going to work or behave like this, that should be good enough for us. However, we do take a lot of information from this solid state chemistry and solid state physics. As a matter of fact, before this in material science came in about some 45 years back, we were talking about the metallurgy, where metals and alloys are being talked about. We are talking about the ceramics, physical ceramics, where we are talking about the ceramics and silicates, oxides, glasses, and polymer science, where we are talking about the polymers. In turn, the material science has an interaction with all these three subjects, but in the science what we are studying here is the relationship between the structure and property, what I simply call the structure property relationship in materials. When I say the word structure here, I do not mean the structural application which I described just now, a building or a body of a ship or a body of an automobile or a bridge. Those are the structures we call, but this structure, when I refer to, is the internal structure of the material. How is it related to the property or the behavior of the material? Here I have just given an example. I have taken two cylinders of mild steel, one as I received from the market, that is on the right hand side, and the other one as it is, I put this in the furnace for annealing for half an hour, and after it is annealed I test it like the other one. I am compressing it in a machine. I reduce the length of the cylinder to 50%, but you see the deformation in the two is very different. One is giving, as received, gives me rings after rings after rings. It's called the concertina mode of deformation. Other one is giving me diamonds, making triangles. One triangle, the other triangle, and then two triangles make a hexagon. If you go through this cylindrical hole, it will look like a hexagon. What is different in the two is also seen here in the stress strain curve of the material. In the case of as received, the deformation goes on very steeply and then comes down rapidly, while in case of annealed one, it right here it starts to yield, and the yielding goes on, and then it takes over the strain hardening, then deforms a lot before it fails. It deforms less before it fails. The as received, the annealed ones deforms a lot before it fails, right. As far as the internal structure is concerned, the difference between the two internal structures is shown here. The one which is as received, it's little smaller the grain size of the material, distribution of the another micro constituent, that is pearlite, is finer as compared to the one which is annealed, where you can see these black portions which are pearlite, they are coarser in size, and the grain size also much bigger than the grain size in the as received one. This change in internal structure has caused this change in behavior. That is what I mean by structure property relationship. If I understand this relationship, then I will be able to use my materials to the maximum advantage as an engineer. Now coming to the internal structure, first level is the macro structure, what I see with the naked eye, or at the most I can use a magnifying lens which is maybe 5 times 10 times, and I can read probably in between these lines, or I can see the scratches onto the surface of the metal or the plastic. This is what I mean by macro structure and the use of the naked eye. Well, resolution of the human eye is 0.11 millimeter, as you know. So anything which is closer than 0.11 millimeter I cannot see with the naked eye. The two objects are placed closer than this, I cannot distinguish them as two different objects. Then second level is the microstructure, one I showed you for the steel just now. To see this, I have to use an optical microscope, and the specimen of course has to be prepared, polished, etched before I can see it under the microscope, and the magnification normally used are 400, 600, 800, but you can go up to 1500. That is the limit of optical microscope, I cannot magnify beyond that. And we are able to see the microstructure as I just showed for the steel. Third is the substructure of the material, which is at a still lower level of few tens of angstrom. I want to see what is happening in the material. Magnification can go up to 1 million, and the device used to see this is called an electron microscope. Electron microscopes are different kinds. Scanning electron microscope, it simply scans the surface of the material, opaque material, and tells you what is the surface like. Depth of focus is very high, and I can use the transmission electron microscope where the material to be used is very thin, so that the electron beam can pass through the material. So solid metal or an alloy, if I have to put, I have to thin it down to a very small, in the range of fraction of a micron. Usually what we do is make a thin disc in the range of about 30 to 40 micrometer, and then with the help of jets from both sides attack it with this acid or a mixture of acids, so that a hole is formed on this disc. When the hole is formed with the help of jets, you will see the edges of the hole will be very, very fine, and those are the edges which we try to see through the transmission electron microscope. Means I am trying to go down to very small distances, that is of the order of 10 angstrom or so in the electron microscope. If I want to see further, maybe I need field ion microscope, where possibly I can see the arrangement of atoms there. But generally, to see the arrangement of atoms in the solid, the crystalline solid, we have to see indirectly the crystal structure, as what we call, through the diffraction. Most commonly we use the X-ray diffraction. We can also use the neutron diffraction and the electron diffraction. Only thing is, the particles which are behaving like a wave, or the X-rays which we are using, their wavelength should be the same order of magnitude as the spacing between the atoms, so that I can get the diffraction, and we will see this in this course, how with the help of X-ray diffraction we can try to conclude what are the simple crystal structures in metals like copper, aluminum, iron, etc. We should be able to see that. Then if I go further down, I try to see the electronic structure, for which I need spectroscopes. That means atoms, we are seeing the inside of the atom now, is a nucleus, around that there are electrons orbiting on different orbitals, right. You have read about s orbitals, p orbitals, d orbitals, 1s, 2s, 2p, like that, 3s, 3p, 3d, and so on and so forth. This is what you have seen in chemistry, this electronic structure, and you need the spectroscopes to see that. Then inside the nucleus you have to see what are the neutrons, protons which are present. You need the nuclear magnetic resonance or the Mossbauer spectroscopy to see that. But in this course I shall be spending more time on 2, 3 and 4, that is why I have put them together, and 1, 5 and 6 I have kept them apart. We will be studying 2, 3 and 4 in this course, because these are the ones which are mostly affecting the properties, particularly the mechanical behavior of materials. We will need electronic structure to some extent when we talk about electrical properties, but not to a great extent. Again we will need them something when we try to talk about the magnetic behavior of materials, but that information we can draw what you have done in school chemistry. We shall start in the opposite direction. We will start with the crystal structure, go to the substructure, then to the microstructure of the material, before we try to see how can we change the structure in the material, how can we process this change in this material, and then we shall like to look at the behavior of the material and relate it to the structure. Then once I know is it possible for me to change the structure, then you see the whole spectrum is available with us. I am given a material, I want to put it to a certain application, I need that kind of a property, its structure is not suitable, I convert that structure to a suitable structure so that I get that property what I need. Or else I know the property, I must have that kind of a structure, I must find a material which has that kind of a structure. I'll locate that material and use it. So that is all what we will be able to understand with this. And among the properties which we shall talk about, this is mechanical behavior, is the response of the material, which is when a mechanical force is applied to the material. First of all, there is a temporary deformation, what we call the elastic deformation. Then there is a change in shape which is permanent, we call it plastic deformation, and ultimately the material fails, I will call the fracture or failure of the material. And electrical properties we shall look at. Conductors we use for conducting electricity, like copper and aluminum wires are used mostly. Then we have superconductors. Well, we have certain limitations in the use of the superconductor, we shall see those. Then the semiconductors, mostly of course the chips which we are using, and then the magnetic behavior of materials. These are the properties which we shall try to look at in this course. With this introduction, before I start with the crystal structures in materials, I shall like to recap a few concepts on equilibrium and kinetics which you have done in school. Okay. All right. So, few concepts on equilibrium and kinetics. Why it is important is, materials, unless they are in equilibrium, unless they are stable, we will not be able to put them to use. That is why, and these kind of concepts I shall be using again and again in the course at different places. So that is why I think it is better for us to revise that. Equilibrium I try to explain with the help of a rectangular block. Probably you have done it already in school. A rectangular block lying vertically on the floor, and then it is tilted. It passes through a stage where the center of gravity again passes through, is within the base, and then it is toppled, lies onto the longer side. In this case, what is happening is, if you look at carefully, it is the potential energy of the block, rectangular block, which is changing. It will remain in the first position if I do not disturb it. It shall remain in the third position also for a long time if I do not disturb it. But it is very difficult for it to live in the second position, even though it is center of gravity passes through the base. This is what I have shown here in another picture, where I have on the y axis the potential energy of the block, and on the x axis the configuration of the block. The first position is here, and potential energy you can see is at its minimum. There is a minimum here. Then position 2 is there, there is a maximum there. Position 3 is here, again a minimum. Locally this is a minimum, locally this is also a minimum, but overall potential energy of this is lower than the potential energy of this one, right. This I express in terms that this, rather the slope of this energy configuration curve, and I say that at equilibrium, which is at position 1, 2 and 3, an infinitesimally small perturbation does not change the energy or the state of the rectangular block. Infinitesimally small, in mathematics while talking about calculus, told while finding out the derivative, the limit delta x tends to 0. When I say limit delta x tends to 0, that is what I mean by infinitesimally small. In other words, if you look at the potential energy configuration curve, the slope there at the 3 places is 0, but the 2 places I have a local minimum, by the third middle position I have the maximum. Out of these, the stable equilibrium is in the position 1 and to some and position 3. That is what I say. If I disturb this rectangular block or perturb it a small, I am not talking infinitesimally small, delta x not tending to 0, I am talking about delta x now. So I give a delta x disturbance like this one, you can see here, it remains. That is what I mean, disturb it, it comes back. But in the position 2, if you do that, it will not come back, either it will go to position 1 or it will go to position 3, it will not stay in position 2. So in these 2 locations where I have local minimum, it is in the stable equilibrium, while at the maximum potential energy it is though in equilibrium but is unstable. A small disturbance will take it either to position 1 or to the position 3, right. If this is not so, the material is unstable, that is if it is not in the local minimum. So when there is a minimum energy, it is a stable equilibrium, when it is a maximum energy, it is an unstable equilibrium. Well, among the stable equilibria, I distinguish the one which is globally minimum is most stable, like among 1, 2 and 3, 1 and 3 are the minimum, but 3 is lower than 1, that will be more stable. But if there are more than the 2 positions like that, third one, if that is the lower one, that is the most stable. So most stable is the one which is the lowest energy, and where I have simply the local minimum which may not be the global minimum, I simply call it the metastable equilibrium. Metastable equilibrium is very important for material scientists, because by and large the materials we use are in their metastable state, they are not in their most stable state. The most stable state of iron is its oxide Fe2O3, that is how it is found in the nature, right. Most stable state of aluminum is again its oxide. Maybe for copper it is sulfide. So the stable state, most stable state is not really of much use to engineer. When I want iron in the form of steel, it is in its metastable state. When I use copper wire, copper in its metastable state. Aluminum is in its metastable state. So the materials which we are using are in their metastable state, and for hundreds of years they can continue to function like that. For my lifetime, if a material behaves like that, for all purposes it is stable. That is the importance of this metastable equilibrium. Getting global minimum energy which for the most stable state, the material may not be of much use to an engineer. Okay, it is not that we do not use materials like that, we do use them. Now talking about this energy, which is maximum or a minimum, what is this energy? You have read something about this also in thermodynamics, and we shall try to look at that today. Among the intensive properties in thermodynamics you have studied are the two, pressure and temperature. An intensive property is the one its value does not change by changing the amount of the material. If the atmospheric pressure is 1 atmosphere here, whether I have 1 kilogram of steel with me or I have 10 grams of steel with me, pressure is the same. That is the meaning of intensive property. Similarly, the temperature, it does not change with the mass or the volume of the material. Then there are properties which change with the quantity of the material, are called extensive properties. One of them you have studied is internal energy. Internal energy we write as U, and this is equal to U0 plus integral 0 to T Cv dt. Now what is U0 here? Internal energy at 0 Kelvin. Physically what does it mean? You have heard of the Condon-Moskov? When two atoms are at infinity, we consider the energy 0. When they are brought together, they form a bond, and this is the distance of equilibrium, this is the bond energy, and this bond energy is a negative number. This is U0. Okay. Then maintaining the volume constant of the material as the temperature is made to rise, Cv is the specific heat of the material at constant volume. You integrate this and you get the internal energy of the material, right. Now coming back to next, the enthalpy is also an extensive property, and we normally depict it by H, and this is written as plus integral 0 to T Cp dt. This is at constant pressure, specific heat at constant pressure. Now what is H0? It's enthalpy at 0 Kelvin. We relate enthalpy and the internal energy through a term which is called PV term. P is the pressure, V is the volume. Well, in solids, PV term is really negligible as compared to the bond energy we are referring to here. So, I can neglect PV completely. This I demonstrate in this slide here. My basis of calculation this is 1 mole of copper at 1 atmosphere. 1 atmosphere is 0.1 10 to the power 6 Newton per square meter, and the volume of 1 mole of copper is 7.09 10 to the power minus 6 meter cube, and that provides me the PV term equal to 0.716 joule. But in 1 mole of copper, if I look at the copper-copper bonds, I will show you this in the crystal structure of copper. Every copper atom is surrounded by 12 copper atoms. So, it forms bond with 12 neighbors. Because a bond is always formed between two neighbors, it is the sharing of bond is half and half by both the neighbors. So, therefore, they are in turn, if I have 1 mole of copper atoms in a solid, I shall have 6 mole of copper-copper bonds, right. So, for 6 mole of copper-copper bonds, bond energy of copper is 56.4 kilojoule per mole multiplied by 6 makes it 338.4 kilojoules. While as compared to the is bond energy of 1 mole, the PV term for 1 mole is 0.716 joule. It's quite negligible, and as an engineer I neglect this. As a result, I say or use internal energy and enthalpy for all my solids interchangeably. When I talk about internal energy, I may mean enthalpy. I talk about enthalpy is internal energy, because the difference is so small it can be neglected. However, when I talk about gases, I cannot afford to neglect this PV term. This PV term becomes very large in case of gases. That is what you studied in school. What you were told in school was absolutely correct, because you are talking about the gases. Okay? But when I talk about my solids, this is a negligible term. Here I show on the x-axis on the x-axis I have temperature, all right. Let me put this in here. I have temperature on the x-axis and I have enthalpy on the y-axis. Whatever the H0 value at 0 Kelvin, as the temperature rises, enthalpy rises Cp dt, and it goes on till there is a change in the solid. It becomes liquid, latent heat of fusion is added, and then it further rises. Now that is the melting point of the solid. Now, as I said, what is more stable is the one which has a lower energy, right. If you look at the enthalpy, if I consider that energy as the enthalpy, Well, first of all, what is our common experience? Below the melting point, material stays as solid. Above the melting point, material stays as liquid. This is liquid and this is solid. Okay. So, free energy of the solid, the enthalpy of the solid is lower in this temperature range as compared to that of the liquid, and that is stable. But what happens above the melting point? Enthalpy of the solid is still smaller than that of the liquid, but what is stable is the liquid. That means it is some other energy, not the enthalpy, which I need to consider for stability in materials. It is not the enthalpy or the internal energy which I can consider, because obviously what my observation is not, I am not able to satisfy that. Let's go back to I think we shall stop here.